I had this wonderful moment this morning. These people I see 4 times a week, but it's all been on Zoom for the past year. Suddenly, 3 of us got together this morning, and we were in the same room, and there were no electronics. It was a wonderful feeling. And not only that, one of them, Leah, has a son who's about 5 years old, and so usually when we're talking, there's Buzz Lightyear going across the screen. And the rest of us offered to put Clinton on Zoom so he could watch Buzz Lightyear. And she's like, no, this is the first time I've gotten away from this kid. Yeah. There are advantages to getting away from your family sometimes. Okay. So where we're at, we'll do lab for week 2 on Friday. Lab for week 2 is not as bad as lab for week 3, which requires a lot of math. You may want to look at it and maybe fill out some of the math before lab for week 3. And we'll get a week off from lab, not this week, not next week, but the following week. Week off from lab and homework. Because that's what my schedule says. Let's see, what else? No exams coming up. You guys just had one, you're good. I got midterm grades in, and the midterm grades are just kind of advisory, let you know how you're doing in the course. There's still exam 2, there's still 3 more labs to turn in, and there's still the final exam. And all of those can help you, or they may pull your grade down. Overall, the grades look okay in here. I'm not too concerned with doing any big curves or anything like that, but we'll see at the end of the semester. Okay, so this is a method. I don't see people doing this a lot with diodes anymore, but they do it a lot with MOSFETs. And getting the hang of this idea, getting it conceptually on this really early stage is still useful. Usually the place where I see diodes used as a signal in circuits are inside a voltage regulator, and most people just buy voltage regulators. Or perhaps if you have an AM radio receiver and you're trying to build it, you can actually take, you know, a kilohertz signal and to get it down to baseband, get it down to audio by just running it through a diode. They'll basically rectify the high frequency signals out as a detector. So those are the analog applications. We're going to look at, well, I guess the more of the power supply applications in here. Yeah. And for the rest of this, and then we'll start looking at the physics behind diodes, semiconductor physics. So the idea here is it's kind of like superposition in 188. Now in superposition in 188, they usually talked about you have multiple DC sources in the circuit, and you deactivate the other sources and find the solution for the rest of it. What I'm going to do here is I'm going to say I have one DC source, and my DC source is this 10-volt source, and I'm going to solve the circuit like the plus or minus 10 millivolts of signal doesn't exist. So this will be my DC solution. And then I'm going to deactivate the DC source and use the information from the DC source. So the DC source, what it's going to do is it's going to put this circuit at some bias point. So it's going to provide enough voltage to those diodes to turn them on or not. So I have to include some information about the DC in order to analyze the AC. So I used, I'm getting through this without explaining all this. I'm going to use the information from the DC solution to figure out what the AC solution is, and then I add them together. It's superposition all over again, with that little twist of the DC bias point will actually affect part of the AC solution. So we usually call the DC part of the solution the Q point, the quiescent operating point. It's just the DC analysis. I took like a senior level elective at ASU, and the professor talked about Q point all the time. I had no idea what he was talking about. And I get the exam in front of me and it says solve, and every single problem says solve for the Q point. I'm like, I have no idea what this is. I go, I'm just going to do the DC operating point. So yeah, try to remember the vocabulary. It might help you. Then once we figure out what the Q point is, we're going to use this to find the small signal parameters. I'll explain that in a minute. In this case, for a diode, it's you calculate a resistance. And then we do the AC analysis and then use superposition to add the two together to get the total result. We do this with MOSFETs when we talk about analog. We do this with op-amp circuits when we talk about analog. We do this with any transistor when we're talking about an analog solution, and even like mixers and weird things like that. Okay, so to get the Q point, I just use the 10 volts. And we're going to use the model of the diode and remind you of this. If the voltage across the diode is greater than 0.7 volts, our model is that the diode turns into a 0.7 volt voltage source. And that is what we replace the diode with. So that would be the minus side, that would be the plus side. This diode turns into this. Okay. If VD, if the voltage across the diode is less than 0.7 volts, we replace the diode. Wherever we see it, it's going to turn into an open circuit. So our first mission here is to look at the circuit and guess whether we have enough voltage across those diodes to turn them on. And if you guess wrong, you usually come up with a ridiculous answer like a negative voltage across the diode or the current through the diode flowing in the wrong direction. And then you guess the other thing. That's the way I do it. But 10 volts on the positive side of these diodes, I've got 0 volts on the negative side, so I've got a higher voltage on the P side. My guess is going to be that they're on. There's one on the homework that, yeah, I can guarantee you'll guess wrong. And you'll see what I mean by that. So I guess the diodes are on. I replace them. I still got 10 volts up here. I've got a 1 ohm resistor. Each one of those diodes becomes a 7 volt source. So I've got 3 of them in series. Still writing, so I can't be frozen. And then I've got an additional 1 ohm load resistor out here. Okay. I don't know anything about the current through the diodes. So I just know their voltages. And I know the voltage on one side of this resistor. I know the voltage on one side of that resistor. I don't know the voltage here yet, or I could figure it out. The easiest thing to figure out is the voltage across a voltage source. So I got 3 of them in series. So this one's 0.7, this one's 0.7 higher, so this point would be 1.4 volts. And this point right here would be another 0.7 of a volt. So this is going to be 2.1 volts. Now I have the voltage on both sides of those resistors. I have the resistance values. I can apply Ohm's law. So we're going to find, I'll call this I1 and I'll call this one I2. I'll call this one ID. I can't get ID because I don't know anything about it, but I can get I1 and I2. So the voltage across the top resistor is 10 minus 2.1. That equals the current I1 times its resistance 1K. So I can solve that. It would be 7.9 milliamps. 7.9 milliamps. For that second resistor here, I know the voltage on the top side and the voltage on the bottom. So it's 2.1 minus 0 equals I2 times also 1K. So this is going to be 2.1 milliamps. Okay, so this is 7.9, and this is where KCL kicks in. If I want to find the current through the diodes, they're in series, they all share the same current. I know the current going into this node is 7.9, and the current going out is ID plus 2.1. I know two of the currents I can solve for the third. The ones of you that will get that will be doing an amazing job in 380. Sorry, I'm preparing myself mentally for the second exam. So I1 equals I2 plus ID. That's just KCL. Draw a little line here. And so ID is just going to be 7.9 minus 2.1 is 5.8 milliamps. We've got all the voltages and current. We've pretty much figured out what the DC operating point is of this circuit. Now, this model right here that I showed you, this is a DC model. The AC model is going to be a little bit different. So the DC model, it's either a short, it's either an open or it's a 0.7 of a volt source. When I go to AC, we're going to look at that curve from the ideal diode equation to figure out what kind of model we can use. So here we go. We've got, this is the graph of an exponential function. It looks like the current ID equals some constant IS times E to the V diode over VT minus 1. And we plot that graph and we get something that looks like this. We've calculated our ID, and the current through the diodes was 5.8 milliamps. So here it is, 5.8 milliamps. And I go across here and I say, okay, it must be operating here on the curve. That small signal, the plus or minus 10 millivolts, is going to be a small perturbation on the input signal. What I'm going to do, instead of trying to use the diode curve equation to figure out what's the current if I go 10 millivolts below that and plug that into that equation, and what's the current if I go 10 millivolts above that and plug that into that equation, and what if it's somewhere in between and I have to plug the whole thing in? No, I don't want to do that. What I'm going to do for my hand calculations is I look at this and I go, ooh, this looks almost like a straight line. And I find the derivative of the current equation at that point. And the slope of that line is going to be 1 over RD. And if you actually take the derivative of the ID equation, you take 1 over it, you get this little RD, and it comes out to be VT, which is KT over Q, divided by the DC current. It's not perfect, but for this whole operating region, we lie pretty close to that line. If I went down to lower voltages, I'd have trouble. But since it's only a small perturbation about that DC point, I can make this approximation. Now this RD, we're going to model it in the circuit, in the AC circuit, like it's a real resistor. It's not a real resistor. It is nowhere on the board. It's nowhere inside the diode. It is the slope of the I versus V curve at that particular point. It's a linear model that makes it easier for circuit designers to do, to figure things out. I've seen mechanical engineers do this. When you're doing, well, electrical engineers usually do this. When you're working a thermal problem, they model the different thermal paths as thermal resistors and actually build an REQ network. It's a different way of just doing a model of what's physically going on. There's no real resistors in there. VT is, for purposes of this lecture, is 25.9 millivolts. On your homework assignments, one of the first things you want to check for is somewhere up at the top, I'll tell you to use VT equals, sometimes it's 25.3, sometimes it's 25, sometimes it's 25.9, but use that number, whatever's up at the top of the assignment or at the top of the exam, because, and it changes depending upon whether you're in temperatures 60 degrees or 80 degrees, it changes a good bit. Okay, so this RD is VD over ID. So when I do the AC analysis of this circuit, my AC model of the diode just looks like this, RD. It's little r, little d. So my AC circuit, I deactivate the DC source, so it goes away. I just have plus or minus 10 millivolts. My 1K ohm resistor here. And I've got 3 RDs in series. And then I've got our load. Each one of those RDs, they have the same current going through them. So RD is 25.9 millivolts divided by, what did we say it was, 5.9? 5.8, okay. I'm going to look it up because I'm not going to do this division. 5.8 milliamps. We're expecting that to come out in like a small value of ohms, maybe like 5 ohms or something like that. It's 4.47 ohms. I punch it into the calculator. Approximating before you punch it in the calculator will help you stop making calculation mistakes. So I do that too. What I would do on my exams when I was a sophomore, I punch it in once and then I punch it in twice. If I got the same answer, I was good. If I got a different answer, I punch it in a third time. That's how I, yeah. So our RD is 4.47 ohms. So I put 3 of those in series. 3 RD is, did I do that? Probably not. 13, yeah, I did, 13.2 ohms. So this series network of 3 resistors is, oh great, 13.2 ohms. And then we can go through and do a voltage divider on it. I will be back shortly. This is slide 9.